Alright, hey guys. So today I'm going to talk about the Raylon Criterion. So the Raylon Criterion is a subtopic of the wave optics. And so electromagnetic radiation can act both as wave and rays. And so we see here, let me start the slideshow. You can see that the dispersion of Y light is actually a ray characteristic. And you can see here that light is both a wave and a ray, and so as you can tell, the arrows are the rays and the wave fronts are the waves. And so today, Raylon's criterion is all wave optics, but we'll kind of mention what distinguish why it's a wave characteristic and not a ray characteristic. And so remember, light is a wave. And so remember that when light passes through an opening or a lens or even a mirror that has a diameter way larger than the wavelength, then the light acts as a ray. So if lambda is way smaller than diameter, light acts as a ray. When light passes through an opening or a lens that has a diameter way larger than the wavelength, then the light acts as a wave. So lambda has to be similar diameter, so light acts as a wave. Here's some images. You can play around with sound being a larger wavelength, acting more as a wave. And so that's review though. I'm going quickly over this because we have Rayleigh Criterion, which is our main topic. Now diffraction is when these small apertures and these lights go through it. That causes the bending of the light. And so what it does, the wave bends, and the smaller the aperture, the bigger the effect of the bending. And so this pattern you see of here on the bottom right here, where it's red and black, you see that this is the pattern caused by diffraction. So the central maxima is caused by constructive interferences. The smaller maxima on the side are also caused by constructive interference, and that's due to the aperture being smaller and the wave, the light passing through it. And so the spots where it's black, it's actually destructive interference. And so this is only done with when there's an aperture. And specifically now what we're going to talk about is a circular aperture. And so the same thing you'll see is that a circular aperture has fudgy edges on the side because of those smaller maxima being created. And because the smaller maxima are being created, let me see. I'm going to show you a demo of how it looks. So you see this light over here. You see that it is fuzzy around the sides. The camera has its limitations too. But the center is pretty clear. And now we bring this other light. And you can tell there's two lights, but as we bring them closer together, it's hard to distinguish between each other. So the Raylon's Criterion is the minimal distance or the minimal angle from the camera to these light sources that we're able to distinguish one from the other. So it's the minimum. And so you can tell they're separate, but as they come closer together, it becomes one. And so now it's resolved, but we're looking for the Raylon Criterion, which is the minimal distinguish, the resolution between each other. And so these are caused again by the diffraction that is around. And so when two central maxima overlap, it's kind of hard to distinguish from each other. Our vision is actually limited by this because our pupil can only dilate so much. We're going to talk that about next. Resolution equals distinguish. So the more distinguishable something is, the more resolution it has. Don't forget mirrors are actually a type of opening as well, and they also go with the apertures and the lenses. So it's just another media. All right, and to what degree? There has to be a formula to find out, and there is. And so the theta equals 1.22 lambda over d, which is the angle equals 1.22 over the wavelength over diameter of the aperture. And like I was talking about, specifically the Raylon Criterion is when here we see, let me get my crayon. We see here the intensity of one object goes to the circular aperture and creates this maxima right here. And then the second option, all object also creates central maxima. And the only way that they're resolvable is by having a distance or an angle here where the trough of the central maxima of one intensity meets up with the peak of the other intensity, the other intensity source. And so when those happen, we know that we have our minimal angle. So that's how we get this equation. We know that at 1.22, we are at the trough, which would be where it's resolvable. But it is affected by wavelength. You can tell wavelength is proportional to the angle, and diameter is inversely proportional to the diameter. And so now we will continue. And we will just say again, review Raylon's criterions when two images are distinguishable when at least the center of the diffraction pattern of one is directly over the first minimal of the diffraction pattern of the other. Remember, these are the units. The units are in radians, and that YouTube video is the physics department kind of explaining the same thing but with an example. We won't have time for it, but look at it. Support BYU, right? This is just a picture that's unresolved, so sometimes it's hard to tell far away from mountains that, you know, there's two peaks or one peak or how far the other peak is, because our eyes can only capture so much and distinguish at a certain angle. And so we'll actually talk about that currently now. So I've here pre-drawn all of it. And so now I'm taking account, I'm looking at my screen. I drew two lines over here, as you can tell, and those are as close as I could draw them. I also draw two dots, and so that is the minimal resolution I can see that they're distinguishable, right? And normally I'm at a distance of 0.25 meters from my computer, and the average pupil size is 0.004 meters, right? What we're trying to find is S, which is the distance between the two dots. And so that's our minimal resolution that we can obtain. And so here we use the formula that theta equals 1.22 lambda over diameter. And so we just plug and chug, right? So let's say this is red light, that these lines are red and they're shooting off 400 nanometers. We have to convert those to meters, so we get, not 400, I meant 700, so take that again. 700 nanometers because it's red light, and you multiply by 10 raised to the 9, and then you divide it by the diameter of the pupil, which is 0.004 on average. We get 0.000214 radians, which now I want to know what's the distance between the two, and the way to find it is just having the standard equation of theta equals S, which is the distance between the two drawn images, and R is the distance that my pupil is to the two images. And so we rearrange that and get angle times the distance equals the distance between the two lines or the two dots. So we just multiply our answer of radians, 0.000214 radians, multiply by our distance that I said was 0.25 meters. And so we get 53 microliters of micrometers of distance. And so that's how close they are, or at least to be resolvable, or what notes let me do. So our eyes are pretty precise. I mean, that's tiny. I mean, bacteria is like, what, 1 micrometer, and so we're only 53 away, so it's not crazy. And so now we're going to talk about, wrong page, sorry about that. We have here, what if the pupil increases? What would cause that pupil to increase, and what colors are better seen than others, right? And so we have pupil increasing would increase the diameter of the pupil, right? And that would be caused by dark. So naturally our eyes dilate when it's dark, or we're in a flight and flight response. And so resolution would increase because diameter is inversely related to angle. And then we'll kind of discuss why. And then colors are better seen, is my assumption would be violet, because we'll go back as we increase our here. Let's increase our we're seeing violet light instead of red light, so our wavelength decreases, our theta decreases. Because resolution and theta are inversely related, our resolution increases. Same thing with diameter, right? Diameter we increased at maximal dilation at 0.008 meters. So diameter increases, theta decreases, which increases resolution. And so that's how we know. Now, one last thing that I want to share is just this program that, if you just copy, let me see, I could pull it up. If you just click on it, it kind of shows you the same thing where we can bring, you got to go all the way to the bottom, where if you increase the wavelength, resolution is decreased, right? And so you got to decrease the wavelength to get better resolution, or increase the aperture. So just kind of play along with that, but that's a nice symbol, and so we can get really close. But I won't waste time there. But remember, there's this, and if you're having any difficulty, this helped me out a lot. So pupils increase, we get better resolution. Violet light is better, and so in a dark room, violet light is very resolvable if you were to think about it. Now, some applications I'm going to talk about is microscopes, as you can tell here in this image, on the top image, that it's all the same except that the two lenses, the objective lens and the condenser lens, is what causes, they add up to be the total aperture. So you actually, because they're usually the same, it's just 2 times the diameter of the objective lens. And so it's the same formula, you just divide it by 2 to get the radians. Telescopes, they're similar as well. It's affected by how big the diameter is. And so we can capture, this is the biggest radio wave telescope, and so we can capture various radio waves. And it's huge, and so it captures, it can distinguish radio waves from each other. Cameras works by mirrors, and the biggest main mirror is what limits its resolution. So the bigger the primary mirror at the beginning controls how nice the picture will turn out, how we can distinguish, one pixel from the other, one mountain from the other. TVs I won't discuss too much, but that's another example. Specifically, I want to discuss something crazy, which are disc. Disc actually have kind of explode the limitation resolution. So limitation of disc, I'll kind of explain what disc are. So disc have 4 layers, but the important layer is the layer where you can actually dye. And by saying dye, dyes it a color. That color is black. So that's when you burn a disc, is you create these dye spots. And there are different patterns, and so you get some spaces that are dyed, some that aren't. And the spots that are dyed, they absorb light, which equals 0 in computer language, and the ones that don't have dye, they reflect light, which equals 1. So it's interpreting that pattern 1 to 0, 0, 0, 1, 1, 0, 0, the standard thing. So these lasers hit it, and yeah. The thing is that the evolution to Blu-ray has been very beneficial, because now we're able to distinguish 2 smaller things easier. So now we're able to put more little dyes in the same surface area to create mass information of zeros and ones for the computer to resolve. And so we see here that the CD, and we did that by playing with the Raylon Criterion, where we used red light instead, like maybe a little higher red light, so infrared light. And so we have here Y lambda is really high, but we decreased it to blue light. It's really violet, and so because we decrease lambda, we decrease theta, which increase resolution. Another thing we did also is increase aperture. Remember, it's inversely related, so increasing diameter decreases theta, which increases resolution. So that's why we can fit more dyes, so they're spaced out by 0.6 now, in the same surface area of the disk, instead of that 2.1 micrometers apart from each other. So now we can store a lot more information in the same amount of space. And that's it for the Raylon Criterion. Thank you for staying. If you have any questions, just comment on the YouTube page below, and thank you. All right, I'm going to quit.